Hey everyone, and welcome to Mike Likes Robots. Today we're going to be looking at how to coordinate a robot fleet using AWS Lambda and other services in the cloud. We'll use CDK to deploy a couple of AWS Lambda functions written in Python and Rust so that we can explore how the execution time and the memory limits help determine the cost. Let's take a look at the console. So here we are on the Lambda information page. We can see that you can run code without thinking about servers or clusters. That's essentially what AWS Lambda is. It allows you to define a function and upload it to this service, and then you can run the function on particular inputs for a particular event. You don't need to provision a server or a cluster, it just runs when that event triggers it. It gives some examples of advantages like pay-as-you-go pricing. It means that you only pay when you invoke a function. So if we wanted to build a fleet management system that organized robots and dispatched orders, we could build a Lambda function for each piece of functionality, which only runs when it needs to run, instead of having a constantly online server where we're paying for electricity and processing power that we're not using all the time. The idea of these functions is to track the status of any robots using a database, which we can then use to build other applications on top of. Let's say you've built a booth that contains a robot arm that serves people drinks. Now you want to scale up from one robot to multiple robots, all serving different orders from different customers. And you want your customers to be able to submit those orders online. How are you going to coordinate those systems together? You could put everything on a server, but then you have to have one server per site, and you need to manage those servers yourself. A great way to manage this is to put those functions in the cloud and use a cloud-driven database so that everything is available and always online. In this video, we'll look at how to build those functions using CDK and provision a database to track those robot statuses. Let's try and build a Lambda function that can store our robot status in a DynamoDB table. What we're going to use is this example repository that I've got here, and I'll link it in the description as well. What this sample repository contains is a Cloud Development Kit, or CDK application, that deploys a few different resources into our AWS account. We can take a look at what those resources are once we've cloned it onto an example EC2 instance. Here I've got an example EC2 instance set up, and it's completely clean except for the SSH keys needed to get in. I'm going to walk you through how to set up this example repository and some of the interesting parts of the code before we see it working. So the first thing to do is to install Git so that we can actually clone the repository and follow the README. We can use yum to install Git and then git clone the repository. Then I'll open that repository in this current code window. Now we're here in the README file, which contains the setup instructions. You can follow these offline, and I'll go through them quickly so that you can see them working. First, we've got some tools to install. On yum, I'm going to yum install npm. Then I'll use npm to install CDK. I can check that's working with cdk -- version, and there's the version number. Next, we'll install Rust and the build tools needed for the Rust Lambda function. This command here is from the Rust.up website, which I'll link in the description, but it's just a bash command that installs Rust automatically. We'll run this and use the default installation. Now we can either open a new terminal or use this source command to enable Rust in our current terminal. And again, we can check it works with cargo -- version. Now we want to install pip, so I'll use yum to install pip, and once complete, I'll use pip to install cargo lambda. Cargo is the package manager for Rust, and cargo lambda is a plugin for that, which allows us to build lambda functions using cargo. Finally, for this setup, I'll install GCC so that it's got a linker for building that Rust application. That's all of our dependencies installed. The next step is to set up AWS credentials. Now I'll check these are working with STS getCaller identity, and that's working. You do need the AWS CLI installed for this to work. Now we can install dependencies and run the deploy command. npm install for dependencies, and npm run deploy to deploy our functions. The first time running this, we'll build our Rust function, which does take a bit of time, but after the first build, it's much quicker to repeat this process. Here, CDK is printing out a list of the changes that it wants to make in the account, so just accept this with Y and continue. And with that, our deployment is complete. Now, before we take a look at what it's deployed in the cloud, let's take a look at some of the interesting parts of the source code so that we know what to expect. First, in the lib folder, there's the CDK stack. This is what is defining all of the resources that are going into our account. We can see that it's defining a DynamoDB table. It then defines two Lambda functions, one using Python and one using Rust. And it can define a local path for where to find those functions. For Rust, our build process is creating a zip file with the executable in, and that's what this is pointing to. We can also see that there's an IoT rule per Lambda function. We'll go into more about how this works later when we're looking at the resources in the console. In the handlers folder, there's the Python update status, and we can see that what's happening here is there's a Lambda handler function, which is called by AWS Lambda whenever this function is triggered. It's passed an event object, which can be used to retrieve the name of the robot and the status of the robot that need to be updated in DynamoDB. It then checks if the status is allowed, and so far there's only one allowed status, which is online. And if they're allowed, then it will contact DynamoDB and ask it to update that entry. If we look at the Rust version of this, here we can see that the online status is defined, and we can add more here. And in the main handler function, we can see it can pull out those same status and name fields from event.payload. So it pulls out the status string and it pulls out the name string. Now, one difference here is that we're not checking whether the status is valid in the code, and that's because it's checked by being defined up here. For us even to get to this point, that must be a valid status, so we don't need to check it in the code. It then makes a request to the Dynamo database, and depending on the result, returns whether it's successful or not to the user. So we've got two very simple functions here. All they do is pull the name and status from the input fields, and then update the DynamoDB table. Now let's switch to the console to see what resources have been created. Here we are in CloudFormation, and CDK creates a CloudFormation template to be deployed. So we can take a look at this and see in the resources what resources have been created. We can see our DynamoDB table, which is currently empty. We can see our two Lambda functions. We can see our ingest rules, and we can see some metadata that we don't need to go into. This is the page for the Python Lambda function, and we can see from the function overview that there are inputs and destinations that are possible. We have AWS IoT as a trigger, and that's because what our IoT rule is doing is listening on a particular topic filter, and if it receives a valid event, it will pass it to this function. So our event trigger is an MQTT message from our robot. We can take a quick look here at other possible triggers, and you can see there's a whole lot of them. Lambda is a well-integrated core AWS service. We can also see for Python that the code has actually been uploaded. So if we wanted, we could make changes here and then test them right within the console. Let's go to the test tab and define a test event. We can create a new event and call it test. And then we're going to update the fields. We'll define a name and we'll define a status. And the only allowed status is online. If we set it to anything else, it would give us a failed message that the Lambda has failed to execute. Let's save this and give it a test. Here we can see that the function executed successfully. We've got some log messages, and a couple of the more important fields to look at are 1, the resources configured. This is one of the core pieces of information that determines the cost of a Lambda function. And 2, the build duration. That is how long the function took to execute. In this case, it was a little over 2 seconds, which is a long time, but we'll see this go down as we change the configuration of the memory. Now we can repeat this process with the Rust function. Here we can see the same trigger, and one difference is that we can't see the code for this one, because it's a custom build, and what's been uploaded is an executable, not a script, meaning we can't edit this and rebuild it in the cloud. That's one disadvantage, is a slightly slower iteration time, because we have to go through our deployment and build phase every time that we make an update. We go to the test tab, we can repeat the same setup, and then we can run our test. And again, the function succeeded, only this time, our build duration is 138 milliseconds, down from over 2 seconds to less than 0.2 seconds. This is our first insight to how much faster a compiled function could potentially run. Now we can take a look at the DynamoDB table. If we go to the table and click Explore Table Items, we can see that 2 items have been returned. There's the console robot RS and the console robot PY, both of them with the status of online. This is a point where we could update it to offline, or we could add other tools that are able to read this database and see that, hey, a robot is ready to take an order, or a robot is requiring maintenance or battery charging. Finally, we can take a look at the IoT rules that have been created. We can see the robot ingest functions. What these are configured to do is, if this topic filter happens, robot/something/status, then it will trigger the linked Lambda function, which causes it to execute. We can test this out either by using the MQTT test client to publish a message, or I've built a script into the repository that will do it for us. So let's switch back to VS Code and run that. So first we need to chmod it, and then we can run it with /scripts/send-mqtt.shell. Now that won't print anything out, but if we go back to the console and take another look at our items, we can see that fake robot has appeared, which was generated by sending an MQTT message to robots/fake robot/status. That caused both of our 2 Lambda functions to trigger. From this, we can see that our robot software could incorporate an MQTT connection to AWS IoT Core. And when it comes online, it can publish a status message saying, I'm online and ready to work. This is the beginnings of a fleet management system that allows us to use the cloud to organize our robots and dispatch orders to them. Now that we've seen the system working, let's take a look at how we can test these functions out with different configuration. If we go to our Python function and execute it a few times, we can see that the build duration has reduced quite a lot. The first invocation seems to take longer. Let's run a couple more tests. 564 milliseconds, 612 milliseconds. So we can see it's around about 600 milliseconds. Now what we can do is change the configuration by going to the Configuration tab and clicking Edit on the general configuration. Now Python functions tend to execute better with more memory assigned. That might be because there's not enough memory for them to run, or it might be because AWS Lambda scales the available compute power with the memory that's assigned. If you need more compute power for a function, even if it's not using all its memory, assigning it more memory will give it more compute power. Let's save that and give it another few tests. The first one is still 530 milliseconds, quite high, but the first invocation takes longer. So let's run it again. And here we are, 139 milliseconds, 148, 153. So we can see that by increasing the memory allowance, we can reduce the build duration quite a lot. What effect this has on the cost we'll explore in a moment once we've seen the corresponding increase in memory for the Rust function. In the Rust function, let's do a few invocations and take a look at the kind of times we're seeing. Build duration 140 milliseconds. Run another one, and we're down to 19 milliseconds. 17 milliseconds, and 5 milliseconds. So it's reduced quite a lot. 5 milliseconds is already a lot faster than the equivalent Python function. So here, again, we're starting to see the advantages of using a compiled language. Even though it might be slower to iterate on, that extra effort might pay out when it comes to the cost of the Lambda function because of the reduced memory requirements and the reduced execution time. Let's increase its memory allowance and see what effect it has. We'll update it to 512 megabytes and save that, and then run a few more tests. First invocation is 69 milliseconds, then 5 milliseconds, 5 milliseconds, and 5 milliseconds. So you can see this is really much more stable now that we've assigned it a bit more memory. With all of that, let's take a look at what the cost of running a Lambda function is using the AWS pricing calculator. What we can do is create an estimate. I'm going to use my region, US West 2, and I'm going to search for Lambda. I'm going to click without free tier so that we can see the cost would be after a year of use. The architecture is set to ARM because generally ARM costs less than x86 with AWS. and we can compile our Rust function to ARM using that Cargo Lambda plugin. So we'll use ARM for our cost estimate. For number of requests, I'll assume 100 per minute. And that's to allow for a whole system setup where customer orders are coming in and being dispatched to robots and robot statuses are being updated. This is a rough estimate, but it gives us an idea of price comparison. Now let's say that we're using Python with 128 meg, which took around 600 milliseconds we saw from our test. So we'll enter 600 with 128 megabytes of memory. And we can see down here that the monthly cost is $5.26. That means that for 100 invocations per minute for a month, the Lambda cost is $5.26. If we set it to free tier, just to experiment, that drops to 0. That would be entirely covered by the free tier of AWS. Let's do a bit more of a comparison. We'll up the memory to 512. And we saw that the duration of the request in this case dropped to around 140. And in that case, our cost drops to $4.97. And that's a useful thing to know because it means that assigning more memory doesn't mean that we're going to spend more money. That extra memory reduces the execution time, which might pay off. And in this case, it did pay off. It's actually cheaper to run the Python function with more memory so that it responds faster. That means that whenever you're trying to create a Lambda function, it's worth experimenting with a few different memory sizes to see what the optimal price point is. For Rust, we saw it was about 17 milliseconds at 128. That drops our cost to $1 per month for 100 requests per minute. If we again compare by changing this to 5 with a 512 megabyte allocation, our cost is now $1.03. That's because although we're using 4 times as much memory, we haven't reduced our execution time by a factor of 4, which is what determines the cost. So it's actually costing us slightly more to use that extra memory allowance. Really what's happening here most likely is that the Rust function is being limited by how fast DynamoDB can respond, which means that it's not our execution time that matters, it's the speed of DynamoDB. So we might as well assign less memory and use a slightly higher execution time. The main points to take away from this are that execution time and memory used are the biggest factors in determining Lambda cost. We've seen that it's pretty cheap per month to run quite a lot of invocations, even though this is only the Lambda cost, not the cost of the other AWS services used. And we've also seen that using Python instead of Rust could increase our costs because the execution time is slower and the memory requirements are higher. So there we have it. If we need to scale up from one robot to multiple robots working on the same task together, chances are we'll need some kind of central management system used to coordinate them. We could use a server deployed to do that, but a good way to coordinate those systems together is to use the cloud. AWS Lambda is one of the cloud services from AWS that allows you to execute different code functions that you define and build and upload in advance, and then set to trigger on particular events. We saw how to build 2 functions that are triggered using MQTT messages on different topics, that are routed using IoT rules. From that, we were able to get 2 robots coming online to report their status as online. We saw that AWS Lambdas have 2 major factors in their cost, which is the memory used and the execution time. And by reducing both of those factors, we can reduce the cost of Lambda overall. Defining Lambdas using a scripted language like Python is great for iteration and developing quickly, but might take longer to execute and require more memory to do so, meaning that it will cost more for those frequently run functions. So for those, we might prefer to use a compiled language, such as Rust, or Go, or C++. Finally, this system serves as a basis for future expansion. We could build a whole fleet management system using completely serverless technologies like Lambda and like DynamoDB to manage our robots and our drink ordering booth systems. Thank you for listening. I hope you try out the code for yourself, and I'll see you in the next one.